Okay, in this video we're going to discuss logarithms, and before we get started I just want to point out the two most important things to know about logarithms. First of all, you want to know that a log is an exponent. No matter how complicated the problem might be, never lose track that you're really just doing rules for exponents, and a log is that missing exponent that you're trying to find. And number two, we want to know how to move in and out of log form and exponential form. So log form looks like this: log base b of x equals y. This is what we call logarithmic form. And sometimes we'll have expressions written in logarithmic form. And we should be able to move pretty seamlessly into exponential form, which will identify our base, it's b. We'll identify our exponent, and remember the log is the exponent, so y here is our exponent because y equals the entire log. So say b to the y equals x, that's exponential form. These two statements are identical, they're just two different ways of looking at the same type of problem. If I write log base b of x equals y, I really mean b to the y equals x. I would say about 9 out of 10 times that you get stuck on problems switching from log form to exponential, or switching from exponential form back to log will do the trick and help you figure it out the rest of the way. So before we look at some examples, some log rules and then some log facts. There's three major log rules that we'll start off with, and then we'll prove a few others. Starting with the product rule, the log of a product is the sum of the logs. The second is the quotient rule. The log of a quotient is the difference of the logs. And then the third rule, which is really just an extension of the first, the log of a power, x to the n. It's the product of the power and the log. Learning those, write them a couple times, say them like I just did there. The log of a product is the sum of the logs, and you'll learn them pretty quick if you don't know them already. Now some log facts, and I call these log facts because they're really helpful just to recognize and figure out really quickly. The first is log base b of b. What could that be? Well, we're saying b to what power is b. No matter what the base is, that answer will be 1. Log base b of b is 1 because b to the first power is b. b to the first power is b, if we're switching to exponential form. Number 2, what could log base b of 1 be? Well, now we're asking b to what power is 1? Anything to the 0 power is 1. No matter what the base is, b to the 0 power is 1. Number 3, b to what power is b to the x? Well, that's an easy one. b to the x power is b to the x, because we can see the exponent right there in the statement. The fourth one's not as easy to think about while you're talking it through, but the lesson that we learned from number 3 is that logs and exponentials are inverses of each other. Here we have a log base b and an exponential base b, and when they work together, well, the exponent x was all that remained. We do the same thing here, an exponential b to a power mixed together, I guess I should say composed, with a logarithm base b, what's going to be left is just x. So these two are a consequence of logs and exponentials being inverse operations. Okay, our first example, we want to simplify log base 3 of 9 root 3. There's a couple different ways you can do this. I'm going to do it just by trying to take this argument 9 root 3 here and rewriting it. So let's see what that would look like. Log base 3, we know that 9 is 3 squared, and I know that the square root of 3, the square root means the half power, so this is 3 to the 1/2 power. Okay, and then what I can do is I can put these together under the same base just by adding their exponents. So exponent rules, like I said before, are very important here. So this becomes log base 3 of 3 to the 2 1/2 power, or 5/2 power, 2.5, however you'd like to write it. Now this question says 3 raised to what power is 3 to the 5/2? So our answer will be the 5/2 power. That's what it equals. And we're done. We've simplified it completely. Example 2, a similar problem. Log base 8 of 1 over the cube root of 4. So I'm going to try to work this out in the same way. I'll have log base 8. Now the cube root of 4, that means 4 to the 1/3. But since it's in the denominator, that's a negative exponent. So this is log base 8 of 4 to the negative 1/3. You see again, those rules for exponents are really, really important. Well, 4, that's really 2 squared. So I'll say log base 8 of 2 squared raised to the negative 1/3 power. There's another set of parentheses. When you raise a power to another power, you multiply. This becomes log base 8 of 2 to the negative 2/3. Okay? So I tried working this out the same way I did before, but I can't get this base and the base of the argument there to agree. There's another rule that we'll learn in class in a couple days that'll allow us to do that. But in general, when you get stuck in a problem like this, what you can say is, hey, that log's an exponent. What exponent could it be? Let me just call it x. And then usually from here, switching to exponential form will allow you to work your way out. 8 to the x power is equal to 2 to the negative 2/3 power. Base to the log is equal to the argument. All right, now what I say, I can get these bases to agree because 8 is 2 cubed. So the left-hand side is really 2 to the 3x. 2 cubed raised to the x is 2 to the 3x, and then the right-hand side is 2 to the negative 2/3. And now I can just argue 2's raised to a power on the left, 2's raised to a power on the right. Those powers must be equal. So I can say that, therefore, 3x equals negative 2/3, and this x, this thing I was trying to simplify all along, is just negative 2/3 divided by 3, negative 2/9. We'll learn another way to do that problem without setting it equal to something, since after all we weren't asked to solve, after we prove another rule for logs that can rearrange that base there. Example 3, something a little different. Now we're asked to solve for x. Okay, so we can see that x is in the argument of both logs. Those logs are added together, and I know that the log of a product is equal to the sum of the logs. That means the sum of the logs is equal to the log of a product. So I can say log base 2 of x plus 5 times x minus 1 is equal to 4. Okay? Rewrote it as a product. Now I can get out of logarithmic form into exponential form by saying 2 to the 4th is equal to the argument there. Here's my argument, x plus 5, x minus 1, that's equal to 2 to the 4th. And 2 to the 4th is 16. Okay, now I have just a quadratic equation to solve instead of a logarithmic equation to solve. When I get the solutions to this, I'll have the solutions to that. Let's work it out. So this is going to be x squared plus 5x minus x plus 4x minus 5, then minus 16. Skipping a few steps there, I hope that's okay. Then we'll factor x and x. Our product is negative 21, our sum is 4, so I think that could be plus 7 minus 4. 3. That's so good at factoring. Which means either x equals negative 7 or x equals 3. We check them both by plugging back in, making sure we don't end up with any negative arguments. Since a log is an exponent, you can't have an argument be negative because you can't do an exponential operation and end up with a negative number. So this negative 7 here, that's an extraneous solution. Cross it out. X equals 3. That works. 3 plus 5, 3 minus 1, both positive, both work when you do the arithmetic. Okay, another example. This one, as it's written, doesn't look like a log problem because you don't have a log written anywhere. But you can see the variables in the exponent, and that's like the most important use of logarithms is solving equations where the variables in the exponent. One way we can solve this equation is switching to log form right away. We'd say log base 2 of 5 is equal to x plus 1. Which means x is equal to log base 2 of 5 minus 1. Now keep in mind that 5 is in the argument, but the 1 isn't. And that's our solution. Sometimes you might be asked to approximate that solution. You can use a calculator. You can use the change of base rule, log 5 divided by log 2 to work out log base 2 of 5, and then subtract 1. So we can see our solution for x is about 1.32. In fact, if I do 2 to that answer that I just got plus 1, I should get 5, because 2 to the x plus 1 is equal to 5. So it worked out. You can check your solution even if it's really, really, really ugly. Since I did that problem pretty quickly, here's another way you could do the same exact problem. Instead of rewriting in log form, you get 2 to the x plus 1 equals 5. What you can do instead is you can take the log of both sides. And when I do it here, I'm going to use the natural log, because that's something we're going to need to get a little more familiar with. There's the natural log of the left. There's the natural log of the right. Since I did the same thing to both sides of the equation, everything's fine there. Now, the x plus 1, the variable's in the exponent there, I can pull that down because the log of a power is equal to the product of the power and the log. So this becomes x plus 1 times the natural log of 2. That equals the natural log of 5. Now what I'll do, divide both sides by natural log of 2, subtract 1, I've got my answer. X equals the natural log of 5 divided by the natural log of 2 minus 1. And you can see that's the same exact answer as I got before. Natural log of 5 divided by natural log of 2, and then subtract 1, 1.32 and some change. Okay, last example. These problems are just sort of little puzzles that you have to do occasionally involving logs to show that you know the different rules. Let's say we know that log base b of 2 is x, log base b of 5 is y, and log base b of 6 is z. Could we find some other log? Log base b of 12, b. Well, I know that 12 is 2 times 6, and I know that the log of a product is the sum of the logs. So log base b of 2 plus log base b of 6. I know 2, that's x. I know 6, that's z. X plus z is my answer. You might be tempted to write x plus or x times z or something like that because it's 2 times 6, but we know the log of a product is the sum of the logs, so that ends up with a sum. Could we find log of 3? Well, 3, that's 6 divided by 2. So now we have a quotient. And the log of a quotient is the difference of the logs. Log base b of 6 is z. Log base b of 2 is x. So z minus x is our answer. Again, these problems are really just to show that you understand how to use those different rules for logs. What about 600? Yikes. So 600, that's, well, it's 6 times 100. And 100 is 10 times 10. And 10 times 10 is 2 times 5 times 2 times 5. So 2 times 5 times 2 times 5. Okay, so I broke it down to all 6's and 2's. And we know that the log of a whole bunch of products is going to be the sum of a whole bunch of logs. So I'll have a 6 that's equal to z. I'll have a log of 2 and another log of 2. Those are each x's, so 2x. And then I'll have a log of 5 and another log of 5 added together, so 2y. Okay, so there's some introductory problems on logarithms, and that's it for this video.